Part 3. So we just saw probabilities always between 0 and 1 inclusive, so you can see 0, you can see 1. The sum of all the probabilities will always be 1, so long as you got all the outcomes accounted for. And if you see a probability of an outcome equal to 0, then that event A, that outcome, is impossible. Can occur. Now, one thing to note here, and this is a very important note, empirical, when you're running the experiment and then counting things to form probabilities, it's not always true. For example, if you're looking at a situation where you have a 20-sided die and you roll the thing a bunch of times, you never see a 5 in your data that you collected. You wouldn't say a 5 is impossible because there's still a 5 on that die. Maybe you just needed to roll it more before that 5 came up. I would certainly check the dice a little if you rolled it 100 times and didn't see a 5 show up ever. But it's still possible that you could see it. So sometimes in empirical, you always have to take this 0 with a grain of salt and be like, maybe I just haven't seen it yet. But if you're talking about something like, I have a 20-sided die and I want to know what the probability is for getting a 21, well, that's impossible. There's no way, there are no outcomes that will ever satisfy that 21 showing up when you roll a 20-sided die. So then it is truly impossible. You'll never see it. So just kind of keep that in mind with that one. That's sometimes the empirical, you don't want to think about it as impossible, just maybe hasn't happened yet. Highly improbable. But with theoretical, if you ever compute it and get 0, then it's certainly impossible. Now, if P of A equals 1, then that event A is certain. So again, even with the empirical idea, this might not always be true. Maybe you didn't see something that would take it away from always happening. Like if you're in Seattle during the rainy season and it's like, the probability it's going to rain tomorrow based on these data I've collected in the last 2 weeks, it's 100%. It's certain it's going to rain tomorrow. Maybe, the next day it doesn't rain. So it's empirical. It kind of throws a different spin on these. But if you were saying something like on a 20-sided die, what's the probability I'm going to get a number 1 through 20? Well, that's certain. That's 100%. You're going to get some number between 1 and 20, if you're being inclusive for sure. All right, so just kind of keep that in mind there. Now, complements. Complements can be used to find the probability of something not occurring if the probability of occurring is known. So a complement here has nothing to do with you tell somebody they look good or whatever. That's not how complements work in probability. It's more the idea that together they make the whole, so that's, they complement each other in a way where together they make a whole, and that's what you want to think about it as in the formula. So the complement of event E, denoted by E with a bar over it, E complement as it's read, you might be saying, why don't they call it E bar? And I guess probability people are more creative. So you read that as E complement. Sometimes you'll also see this, I've seen it in other places where they'll do E with a little superscript of C to make it a little bit more clear that it's complement. But E bar works as well. And, the complement is just the set of outcomes in the sample space that are not in the event E. So the probability of E bar is given by 1 minus the probability of E. So it's two sides to a story. You either have the event or you have the complement to the event. Now there could be more outcomes in one or the other, but it's still, you put them together and you get the entire sample space. So for example, if the probability of randomly selecting a green ball out of a bag that has 3 red, 5 green, and 4 yellow balls in it is 5/12, so the probability of green equals 5/12, then the probability of selecting a ball that is not green is 1 minus 5/12, and this would end up equaling 7/12. So together, notice the two, when you add them together, you get 1. So, and that'll always be the true, because you're subtracting from 1 in order to get the value. If you add them together, you'll get 1. The event and its complement will always add together to be 1. So what I want you to do is try this one. Go ahead and pause for example 2. All right, so you pick one card from standard deck 52. What's the probability of the following event? Picking a card that is not a king. We found the probability of a king earlier was equal to 1/13, 4 out of 52. So the probability of not a king, the complement to the king, would be 1 minus 1/13, or 12/13. All right, so then last little thing here we're going to look at in this section is probability distributions. And as I said, it's a lot like a relative frequency distribution. In fact, if we didn't use a different name, you'd probably easily confuse them just by looking at them. So a probability distribution for experiment is a list of all the possible outcomes, like what you gathered in your sample space, and their corresponding probabilities. So in this example here, consider the probability distribution of the number of boys when 5 babies are born. Answer the following question according to the probability distribution. Notice that all the probabilities do add up to 1. That's how you can always check and see if you have a valid distribution. All these little probabilities in the column there should be equal to 1 when you add them together. So what is the probability at least 4 of the babies will be boys? Enter your answer as a decimal. Do not round. Let's go ahead and try that. Okay, so at least 4 of the babies. So at least means 4 or more. So at least is greater than or equal to 4. So we're going to come up here and look at greater than or equal to 4 would be the 4 and 5. So we're just going to take this probability of being greater than or equal to 4, and that's going to be equal to 0.15625. We just add together the probabilities for the individual outcomes that were listed to get the probability of the event. So this 0.03125, and this will equal 0.18750. That's all there is to it. You just got to look at the table and pick the right things. So this next one then, last one here, similar idea, but now we have to do something in order to get to the probability. A little bit more than just look at the table on its own. So we have a frequency table that's being given now. And what is the probability that a randomly selected person from the sample is 35 years or older? Let's go ahead and try that by pausing. Welcome back. So if you said, I need to figure out the total so I have a denominator, because if we're making a fraction like you always do for probabilities, you need a denominator for the total number of outcomes, and that's always the sum of the frequencies, then you're in a good place. If you didn't do that, then hopefully you're going to do it from now on. But at any rate, you add together all these different frequencies and you get a total of 57. So that immediately is my denominator. Now for 35 years or older, that is greater than or equal to 35. And looks like the only one that satisfies that is this one right here. So the probability of being greater than and actually we'll go ahead and use the x here since that's in there, our random variable x greater than or equal to 35 would be equal to 14 satisfied that event and 57 total. So your probability is 14 out of 57, and that's reduced as much as it can go. Okay, so that's 3.1. A lot of terminology there, a lot of concepts, but hopefully again you realize you're just making fractions, and as long as you make those fractions in the right way, you can make these basic probabilities. So if you have questions, please ask, and see you in the next video.